Welcome to the Introduction to Rational Exponents. So let's recall some exponent laws that we have been introduced to a long time ago. Recall the law that a to the power of m times a to the power of n can be written as a to the power of m plus n. Now, this is called the product law the product of powers law. That is, you simply add the exponents when the bases have to be the same, though. So consider now that we're just going to say 4 to the power of 1/2 times 4 to the power of 1/2. And really, this is 4 to the power of 1/2 plus 4 to the power of 1/2 by the product law. In other words, this is 4 to the power of 1, or quite simply 4. Whereas the square root of 4 times the square root of 4. Now, this is equal to the square root of 16, which is also 4. And I'm just going to jump straight in and simply put any base n, or a, to the power of 1 over n. We can convert that, actually, oddly, into a radical. The bases would stay the same, but if you notice, the denominator has n. The index of our root is also n. So this means that the square root of n can also be written as n to the power of 1/2. So we could write here a to the power of 1/2 times a to the power of 1/2. We could write this as the square root of a times the square root of a, where our index, now notice how the denominator of our rational exponent, rational meaning fraction, was 2, and then we're able to convert it to the index of our root. Now, we have two ways to solve this, and if you want, probably, as we've seen in the above, this is a to the power of 1/2 plus 1/2, so this is a to the power of 1. And that's all good. So the square root of a times the square root of a, well, we could write that. Notice that our index is 2. So here we can flip around our reasoning and simply say when our index is 2, and we want to write that as a rational exponent, well, we just simply make the denominator the same number as our index. So this is a little bit odd, but it actually is going to help us out quite tremendously whenever we look at exponents. So example 1, change the following into to radical form, then evaluate. 9 to the power of 1/2. Well, 9 to the power of half can be written as, now notice that the denominator of our of our exponent is 2. We can change that into the index of a radical. In other words, this is equivalent to the square root of 9, which is 3. 25 to the power of 1/2. Well, my base is 25. My denominator is 2, so that directly corresponds to the index of my root. So it's really the square root of 25, and that is 5. So 25 to the power of 1/2 is 5. And interestingly, oddly, if you enter in your calculator, 25 to the power of 0.5, which is 1/2, it will equal 5. It's weird, right? Like, that's just a weird thought. Anyways. For cube roots, it's much the same. So our cube root, here's our index. Now our index is 3. So I could rewrite this, the cube root. This and this mean the exact same thing, right? So which is easier for you to calculate? 5 to the exponent 1/3 plus 5 to the exponent 1/3 plus 5 to the exponent 1/3. And this is really simplifies as 5 to the 1. Or we could use the product law for the radicals, and we can, it's really 5 times 5 times 5, the cube root of that, and the cube root of 125, well, that's just equal to 5. Pick your poison. But this is really, really important. No matter if it's square root or cube root, some number a to the power of 1 over n, you could write that as the nth root of a. So, example 2. Now I'm just going to, I think the hard thought process might be done. Change the following into radical form, then evaluate. Well, if I notice the denominator of a rational exponent is 3, that directly ties into the index of my root. So 27 to the power of 1/3 is the cube root of 27, which is 3. Now, again, 1,000 to the power of 1/3, well, the denominator of my rational exponent directly corresponds to the index of my radical. So what is the cube root of 1,000? 10. So it says in general, any number a to the power of 1 over n is going to be equal to, can be written as the nth root of a.